So we are in the middle of chapter 17, the last chapter we're going to cover. So we're going to do section 7.3, 17.3 today. I think 4 and 5 tomorrow, and then 6 and 7 on Wednesday, and then Thursday is reserved for the final review. I think since this is the final review, I'm going to go over like the older stuff just to remind everyone, okay, make sure you know momentum, make sure you know how to do kinematic equations, remember those things, how to deal with free body diagram, and I'll talk about all that stuff on Thursday with you guys. Is that okay? Or is that going to be too late? Okay. Thursday is a good day? Okay. All right, so at the end of class today, so we should learn how to calculate this thing called intensity. We actually kind of already learned how to do that on chapter 16. It's the same intensity we learned about wave because, as you know, sound is a wave, right? So therefore, the same calculation applies. And how human perception of sound is quantified. There's actually a slightly different quantification of intensity when we deal with our human hearing versus just, you know, the energy per second that's being sent out by my voice. It's actually slightly quantified, slightly different because human hearing doesn't work the same way. Okay. So from chapter 16, we learned that if we want to figure out how much power is being sent out by the wave, okay, this power has this weird long equation that has a bunch of complicated variables to it, right? It's 1/2 times the density of the string, okay, the amplitude square, the frequency square times the speed of the wave. And the thing that was important that I reminded you last time is that the amount of power being sent out by the wave is proportional to the amplitude of that wave square, okay? If you double the amplitude, you quadruple the amount of power, right? If you make the amplitude 3 times bigger, it's 9 times more powerful, okay? So this is to know that the power of a wave goes up as the square of the amplitude, not just the amplitude itself, okay? So let's say we're trying to represent the intensity, well, we're trying to represent how loud something is. Let's say you got a little gong. So it's like a big metal drum type of instrument, right? And this sound goes out spherically. So if you're near the gong, right, you're gonna have a very loud or highly intense sound at very near the gong. But if you're far away from the gong, it's not so bad, right? So that's why you want to stand far away from it. And this is because, okay, the intensity, the thing we're actually going to feel when we hear the sound is actually the amount of average power sent out by the wave. So this is the thing that's proportional to the amplitude square. Unfortunately, A is used in 2 different ways here, right? Divided by this A down here is actually the surface area, right? I would actually put SA down there, but the book decided not to, okay? The idea of this surface area is that as the wave energy goes outward, right, it spreads out spherically, right? So the further away you are from the source of the sound, the bigger that sphere is, right? Because the sphere grows as 2 pi r squared, right? It grows, a sphere that has twice the radius has 4 times the surface area, right? So the idea is that while the intensity is going to go down as the power, well, it's the power divided by the surface area that we figured out up here, right? So if you want to figure out the intensity of a particular sound and you know the power at the source, okay, at the source, okay, you just have to divide that by the surface area of a sphere, right, which is 4 pi r squared, okay? This is something that we didn't get to do the previous chapter. If you want to compare the intensity at different radius, let's say we're going to call this R1, right? Let's erase this, all right? 2R is equal to R2, okay? Notice that, right? The amount of sound going per area, right? This has some area 1, right? 1 times whatever that area is, right? When you go out twice the radius, now you you have that same amount of sound energy has to cover 4 times that area, right? So actually the sound intensity goes down as the radius square once again, okay? So therefore intensity is also proportional to 1 over the radius square, right? I can actually just derive this for you. Hopefully that makes sense, right? So if you have some intensity at some radius 1, right? This is some R1, right? And you want to figure out the intensity at some radius R2, okay? The way you calculate that is just take the ratio of the 2 radii. So let's say the first radii is, 5 meters, and then the next one is 10 meters. So you put 5 up here, 10 here, right? This gives you a factor of 1/2, right? But then you have to square it because intensity goes down as radius square, right? You square that, so you get 1/4 here. So if you double the distance you are from the sound source, the intensity of that sound goes down by 1/4. Okay. What if you triple it? Anyone know what if you triple the distance you are from the source of the sound? How much would the intensity go down by? Anyone wants to give a guess? Or know what the answer is? So 1/2 gives you 1/4. Okay. Sorry, twice the radius gives you 1/4. 3 times the distance will give you how much, you think? 1/9. Yeah, exactly. So you just have to take that 1 over 3 and you square it, you get 1/9. Okay. So this is how you relate intensity at different radii. Okay. Okay. Or different distances from the source. Okay. We're actually going to do a little work. The worksheet will actually have this. You're going to need this equation for the worksheet today. Okay. So one of the things we want to also quantify is how can we relate the intensity of the wave / power of the wave to the pressure, the change. Remember, when we want to quantify how big, instead of an amplitude of a string going up and down, right? When we quantify sound wave, because it's a longitudinal wave, the wave travel along the direction of the wave propagation, right? We don't have up and down motion. We have compression, right, which gives you high pressure area, and then rarefaction, which is actually gives you an area of low pressure, right? This is quantifying. So instead of defining amplitude, the amplitude is basically this change in pressure, right? So if you draw this, the change in pressure is high here, is low here, right? High here, low here, and stuff like that, okay? So if you go through the textbook, which has a bunch of calculus and a long derivation of I think it's like a full page of derivation, you can calculate that the intensity of a wave, right, is once again, right, equal to the amplitude. Remember this change in pressure, right, is equivalent to the amplitude, right? It's once again, right, proportional to the amplitude square. In this case, instead of amplitude, right, of a string up and down, it's the change in pressure, right, square once again, right? So it's the same type of quantification, right? Right, there's some constants that you're gonna have to figure out from that one page of derivation, but down here, right, this is the change in pressure max, right? Because the amplitude gives you the maximum change in pressure. You can just think about this as kind of like the amplitude of the pressure change, okay? Okay. Down here, this is the density of the fluid, meaning like density of air, water, whatever you're sending your sound through, okay? V is once again the speed of the wave, okay? Okay. So this is how you can actually calculate the intensity of a wave if you know what the maximum pressure changes, aka the amplitude of the pressure change, okay? And then there's this factor of 2, just like this wave on the string, there's a 1/2 in front, right? And then this is the density of the fluid you're dealing with. and v is the speed of the wave traveling through it, okay? So for example, let's say you have a loud stereo that's playing a sound that has an intensity of 1 watts per meter square. So the intensity is 1.00 watts per meter square, okay? Okay, and then we want to find the change in pressure, meaning we want to figure out the amplitude of this wave, okay? If the density of air, which is this letter rho, 1.25 kilograms per cubic meter, okay? And the speed of sound at this particular temperature is 340 meters per second, okay? Just to note that, remember that 1 atmosphere of pressure is about 100,000, okay? So if you find your answer to be like 1,000,000, that's not going to make any sense because, right, when someone produces a sound, that pressure change should be pretty small relative to the actual atmospheric pressure, okay? Because if I'm able to make a pressure change of like 1,000,000, it's going to like kill everyone who I talk to, right? It's kind of like the, yeah, we don't have to go into there's certain things that, yeah, okay. Let's not talk about that. Okay, it's just a fun. Okay, so that's the information we got. Okay, so to find the solution, right, we start off with this long equation, delta P max, right, divided by 2, divided by rho, divided by the speed of sound, right? This is actually what we want as the answer. So we want to solve the equation for that. So if you put the 2 times rho times v times I on the left-hand side, right? Okay, and then you square root both sides, okay? So delta P is going to be, delta P max is the square root of 2 rho v times the intensity. Okay, if we plug all the stuff in SI units, we should be good. Let's see, right? Right, there's 2. The density of air is 1.25 kilogram per meters cube, right? That's an SI units, check. Speed of sound is 340 meters per second. That's also in SI units, check, okay? And then the intensity is 1.00 watts per meter square. This is also in SI units, so that checks off. So all of these should come out with the right units for us, okay? Times 340 times 1, okay? I square root the whole thing. When I square root the whole thing, you get 29.2, okay? And the SI units for pressure is a Pascal, okay? The shorthand for this is the PA, okay? So by playing a really loud speaker, I'm able to exert a change in pressure of about 30 Pascal over 100,000, which is not that much, right? So that makes sense, okay? So this change in pressure is going to be on the order of maybe like 100 to like 1, okay? It's not going to be 1,000,000. If you get 10 million, then you're going to actually be killing people with that, okay, with that sound. Any questions about this example? Okay. All right. Now let's talk about human hearing and this thing called sound intensity level. This is where a lot of people get confused. But so our human ears, well, this is our little ear. There's some little fat cells here, right? Right. The sound wave gets collected by our ear and then gets funneled into our outer ear. Our outer ear is disconnected from our inner ear through this thing called an eardrum, right? It's basically a little thin sheet of membrane, right? When this thing vibrates, it actually causes a bunch of little tiny bones to move, right? And it translates that vibration into this thing called cochlea. Those of you, anyone knows about this from the biology class? Not yet, not physiology. Okay, so this is how our ears actually work. The cochlea is our sound sensor, okay, inside our inner ear. Cochlea is actually a very interesting organ, okay? It's basically this long tube, okay? And it's filled with the cochlea fluid, but on the surface of this little tube, there's a bunch of little hair follicles, okay? These little hair follicles, okay? And it's twisted into a spiral like this, okay? The way it senses sound is that as the sound wave comes in, right? These little hair follicle will start moving, okay? Right, as the sound passes through it. And these little follicles are connected to nerve endings. Therefore, it's actually sending that follicle movement into your brain, okay? Just as like when you feel the wind on your skin, right? You can actually feel kind of your hair moving. Similar thing, but much more sensitive and very tiny inside your ear, okay? So what happened is that very high frequency sound cannot penetrate into the cochlea a long distance. So very high frequency sound gets stopped at the entry part of your cochlea, where the lower frequency with a longer wavelength, right? Those are actually able to penetrate deeper into your cochlea. And therefore, you can actually differentiate different pitches of sound. So this will be, you know, when your brain senses a bunch of hair follicle moving here, it says, that, oh, that's a high pitched sound, right? But when it senses a bunch of hair follicle moving around in here, oh, that's a very low pitched sound that it can hear, okay? And this is one of the reasons why people who are old like me, right, start losing their hearing at the higher pitch, right? Because this gets exposed first to any type of sound wave that you're exposed to it. And this is the part of my ear is probably damaged, right? Probably this outer part, because I can only hear it up to about 15 kilohertz now, okay? I actually play this with my upper division physics students. It's like, which sound wave can, how high of frequencies you can hear. One of my students can hear about 23 kilohertz. So he has like a little bit of super hearing, but he's like the youngest one there, okay? Anyway, I think the whole point of this is that to tell you that the humans do not hear sound in a linear fashion. So how loud something appears to us is not proportional to the intensity value that we've been calculating. We actually hear things in a logarithmic fashion, okay? That means if I want to make something twice as loud, okay, I have to crank up the intensity by a factor of 10. Okay, it's kind of like the same scale as like earthquakes, you know, whenever people talk about earthquake, right? A 6.0 earthquake is actually 10 times more powerful than a 5.0 earthquake, okay? So this is the equation to figure out how loud something is to humans. This is known as the sound intensity level. Put that in here, make sure that's clear, okay? So this is very confusing. There's the regular intensity and then there's the sound intensity, okay? Sound intensity will have this unit called dB. The dB stands for decibel, okay? Okay, and you have to calculate it through this log function. You have a 10 times the 10 base log of the regular intensity level divided by I naught. This I naught is the threshold of human hearing, which is actually 10 to the minus 12 watts per meter, okay? This is the lowest intensity we can hear, okay? So we're relating this all to basically how well people can hear. So here's some example values. If I can go down, right? So let's say I'm just talking to you. Maybe I'm actually louder than this, right? The decibel I'm speaking with is 60 decibel. The sound intensity level is 60 decibel. The intensity of the sound I'm making is 10 to the minus 6, okay? But let's say you're, you know, at a rock concert or something like that, okay? Or you're working in front of a wood chipper or something, okay? The sound level / sound intensity is 120 decibel, okay? That's a really loud sound. But the amount of power per meters, the intensity is actually 1 watts per meter square, okay? Right, notice that, one thing to notice that every time you go up by 10, you go up by every time you increase linearly by 10, so 100, 110, 120, right? You go up by a factor of 10 in the intensity, okay? Something has to be 10 times louder in order for you to increase the decibel by 10, just a linear value of 10. Okay, so let's practice some log math because I'm pretty sure that most of you guys don't do log math. Every day you go to the cash register, you don't have to take the log of, the tax value and stuff like that when you go to the grocery store, right? It should actually, just to get people practicing it, right? Anyway, so let's say the intensity of a particular sound wave is 3.5 times 10 to the negative 5 watts per meters. What is the sound intensity of that? Okay, so to calculate that, we just have to plug it into this formula, which gives you a value in decibel. 10 log base 10 of 3.5 times 10 to the negative 5 watts per meter square. I naught up here is the threshold of human hearing, which is 1 times 10 to the minus 12 watts per meter square. Okay, since this is a definition, right, this denominator here has infinite sig figs, right? It's just a definition. Okay, I do that, e to the negative 5 divided by e negative 12. Okay, take that number, take the 10 base log on it on my calculator. This is a big log number here. Push that. Okay, that completes this part, but you still have to multiply by 10 times 10. I get 75 decibel. Okay, all right, we're going okay. The other way is actually harder because now you have to invert a log function. Okay, so let's say the sound intensity level is 7 decibels, pretty quiet sound. What is the intensity of the sound? Okay, so once again, we use the same formula. The problem is that what we're trying to solve for is buried inside this log function, right? How do I get that? How do I unlog that stuff, right? Okay. So first of all, I'm going to do is I'm going to divide both sides by 10. Okay. Beta equals to 10. 10 base log of I over I naught. Anyone remember their college algebra and remember how to delog things? How do I get this number out of the log function? If I have a cosine function, what do I do to get the argument inside of the cosine function out? Inverse cosine, right? What's the inverse function of log base 10? Exponential. Yeah, exponentiating to specifically to the power of 10. Okay, so if you have log base 10 of a number, usually they call that number A, right? If you exponentiate that to the power of 10, these two functions cancel each other out, and therefore you just get the number back. Okay, so to deal with this, right, we're going to have to take both sides to the 10th, exponentiate both sides to with a base of 10, and these two guys cancel each other out because the log cancels over with the exponentiation. The left-hand side stays the same. Okay, the right-hand side just have the argument that falls out of it. Okay, and therefore I is actually going to be I naught times 10 beta divided by 10. Okay, and we have beta up here, and I naught is the 10 to the minus 12, right? Okay, so let's calculate what that is. And beta is 7 divided by 10. Okay, so 10 to the power of 0.7, right, times 1 e negative 12. Okay. Okay. So the intensity level is actually 5.0 times 10 to the 12. And since this is an intensity, this will have units of watts per meter square. Okay. The thing we calculated previously, right, since it's a sound level, it has units of decibel. Okay. You can actually be able to tell which value someone is talking about. Okay, if it has units of decibel, is this beta thing, right? The sound level, the sound intensity. If it's watts per meter square, it's just the regular intensity. Okay. All right. Ethan, do you want to pass out the worksheet? Okay. So while Ethan is passing out the worksheet, do you guys have any questions about these calculations?